Hi students, in this lecture class we are going to discuss about an experiment which proved some special nature of light. This lecture series is a part of Introduction to Quantum Mechanics. In this introduction, the last two sessions, we discussed how the classical theories of physics fail to explain certain observed experimental phenomena. One of the phenomena is Compton Effect. We'll discuss about this in this session. What is Compton Effect and how classical theory failed to explain it, and when quantum idea was adopted to explain the theory, to explain the experiment rather, how everything fall into place. Okay, this is session number 12 and the title of the lesson is Quantum Mechanics 1, under which we are going to discuss Compton Effect. Compton was an American physicist. In the year 1923, he did a very wonderful experiment and he tried to explain the results of the experiments which he got, and Debye, another scientist, independently gave the explanation too. So let us see what is Compton Effect. When high energy radiation, that is high energy electromagnetic radiation, was made to incident on the electrons which are loosely bound to their atoms, then the X-rays or the incident radiation gets scattered. The scattered radiation had reduced energy and therefore reduced frequency. Now what is so remarkable about this effect is that it confirmed the particle nature of light. Classically, light was thought only in one angle, that it is having wave nature. Okay, let's see what is the geometry of Compton scattering. Now here is the loosely bound electron, which can be considered as free electron, on which a photon is made to impinge. Then the incident photon changes its direction and the target electron recoils. The scattered photon in this particular direction is now different. There is difference in energy and therefore difference in frequency. In terms of wavelengths, the wavelengths become longer. Okay, that was the Compton Effect. Classically, see if it can be explained. So what is the classical theory? When the X-rays fall upon the target electron, it will make the electrons to oscillate, and the electron will oscillate with the same frequency as that of the incident radiation. When it oscillates, an oscillating charged particle is supposed to radiate electromagnetic energy. Therefore, it will once again give out the radiation with the same frequency as that of the incident radiation. This is classical idea. But experimentally, what was observed? Experimentally, it was observed that there are two peaks as the output. One being the unmodified frequency signal, the other one is the changed frequency signal. So, it is also observed the change in the frequency of the incident radiation is independent of its initial frequency. It depends only on the angle of scattering. This otherwise means if you see the scattering in a particular angle, then only the change in frequency can be seen. Otherwise, it cannot be seen. If you keep on changing the angle, the change in frequency also changes. Now, I have put a few pictures over here. So, in these plots, the wavelength of the incident radiation and the wavelength of the recorded radiation after scattering is given, and their intensities along y-axis. So, what was the observation? The scattering and the change in the frequency or the wavelength, and therefore the energy, depends on the angle of scattering. See, here the angle is 0. You have the incident radiation with wavelength lambda, and when you look at the output, the direction where you can observe scattering, in this particular direction no scattering was observed. Okay, but let us come to another angle, that is 45 degrees. Scattering angle is 45 degrees. So, at this angle, see, there is one peak and there is another peak. The higher peak here represents the wavelength of the scattered photon. Okay, and at some other angle, say 90 degrees, see, the scattered frequency, the scattered radiation is becoming predominant, and this lambda dashed minus lambda naught is the Compton shift. See, it is wider over here. Then at an angle of 135 degrees, see, the Compton shift has increased. So, as the angle increases, the Compton shift increases. So, these are all the experimental observations. So, what really is happening in this phenomenon? So, as I have told you, there is, suppose, a free electron. This free electron is supposed to be stationary electron. It is at rest. So, X-ray, being the electromagnetic radiation, is now considered a photon of energy. Okay? When these two interact, the interaction is elastic in nature. collision is elastic in nature. But what happens because of this collision is inelastic scattering. So in this experiment we can see that the law of conservation of energy, not only that, the law of conservation of linear momentum can also be verified. So here in this diagram you see an atom is given as a picture over here, and h nu naught is the incident photon. It is a photon, means it is a particle now with a certain energy h nu naught, and its wavelength is lambda naught, and it is going to collide with a free electron. We can call this to be a free electron because it is loosely bound to the atom. Then whatever the energy that is incidenting on the free electron, that is scattered, the electron itself takes some of the energy. Rest of the energy is scattered in a different direction. The incident energy is in this direction straight, but after scattering it is not going in the same direction as the incident radiation, but its direction changes. Okay, and that angle between the scattered photon and the direction of the incident photon is phi. Okay, and the recoil electron goes in the direction, and it is at an angle theta with respect to incident direction. So developing a theory, Compton said that the radiation that is made to fall on the electron, they are quite strong, like X-ray or gamma ray, and they have the wave nature, but they behave as a particle or a photon having an energy h nu, and because of collision the electron is going to recoil, and its mass should be considered, and its direction should also be considered, and the relativistic change in the mass of the electron should be considered in the derivation, where the Compton shift can be calculated. So developing theory, he calculated the Compton shift and verified whether it matches with the experimental results. So here the we talk about the verification of the result, and we are not going to derive the expression for it. Okay, so we also consider the linear momentum and the angle between the initial and final direction of the photon, and the photon has the energy E is equal to h nu. Okay, so Compton effect is a problem. In this problem, what do we have? We have the collision between a photon, which is a particle, and also a free electron, which is also a particle. So after collision there is a change in wavelength of the scattered photon, which is d lambda, and that is given by the formula d lambda is equal to lambda dashed minus lambda. Lambda dashed is the wavelength of the scattered photon, lambda is the wavelength of the incident photon. Okay, and they depend on entirely on the angle of scattering phi. And here in this particular expression you see the term h by m naught c. M naught is the mass of the electron, c is the velocity of light, h as we know it is Planck's constant. So h by m naught c is called as Compton wavelength. Okay, so when we calculate h by m naught c, substituting the values, the result that we can get is this much. How much is that? 0.02426 into 10 raised to the power minus 8 centimeters. So the previous slide also I showed what is the Compton shift. So using that Compton shift, one can calculate what is Compton wavelength, because we also know what is phi. So knowing phi, knowing lambda dashed minus lambda, in other words d lambda, one can calculate h divided by m naught c. Okay, so the experimental value and the calculated values exactly matched each other. Thus Compton gave the explanation to the observed results, just taking the idea of the particle nature of the incident radiation and also the quantum of energy, which is very important, which has discrete values. Thus Compton could win a Nobel Prize for his discovery and satisfactory explanation in the year 1927. So we can see that coming from classical ideas and getting into quantum ideas, this experiment Compton effect is explained satisfactorily.